Nice to meet you all, but why don't we get started about talking about robotics, which hopefully everyone knows they're here for robotics and machine learning. Great. So there's a couple of topics for today that I'm going to go over. This is really going to be a lot more as like, what's the premise for the class? Like, why are we here? I mean, robotics and machine learning works perfectly, right? It's what everyone sees on the news, besides the fact that people are putting a bunch of money towards it. So obviously there's still something missing. So we'll talk about that a lot through this class and get into the details of like, okay, why doesn't this work? Or what else do we need to get things to work? So, and that's where it's kind of this interesting bit of revolution that's been happening lately, because robotics are not new at all. They've been around for quite a long time. I really like this example here in the bottom, where actually the first humanoid-ish robot is about 100 years old. It didn't do a lot. It kind of stood up and then sat back down. Couldn't find any videos. It's almost like before when cameras were invented, so it was a good while ago. But you can make this kind of mechanical system. But the problem with a lot of current like robotic systems, although it's changing a little bit, is they really only operate in like really controlled environments. Such the fact that like they don't need eyes. They're just doing like the same really repetitive process, like manufacturing a car and attaching doors to the car, something like that. Doesn't really require any intelligence. It kind of like manufactured the process down to such small fault tolerances. You don't really need intelligence anymore. So this is what I mean by doing really prescriptive behaviors. There's nothing they need to adapt to. And they have this really limited ability to adapt. Like even in some like car manufacturing plants, if like a drain of dust comes into the giant building, they have to shut everything down, clean the entire place, and they can only start it up after that's done. So these are really brittle systems, making them not very reusable, not very flexible. Everything that we probably want from these systems. So that's where we want to get to this next step. At least for me, these are some of my, like favorite reasons for why we want to do much better than these systems. So like one, it'd be really nice if we could have more time. Think of all the things you could do if you didn't have to, I don't know, fold laundry, clean your kitchen, mow your lawn, shovel snow. It's probably going to now take more time these days. And I like to give this example, there's a couple of other ones too, but like Einstein was actually just doing math for fun in his spare time because his patent office job was probably just a little bit too boring. But maybe that like thinking creative time is really the type of stuff we want to maximize and make more space for, not necessarily do some of these other cleaning tasks. There's some more interesting ones here too. If you've ever seen online some of those people who put in a lot of effort, but they basically revitalize the whole landscape because they like plant trees and everything for a really long time. And just looking after something and caring for something like that makes a really rich ecosystem. So maybe if we could have a lot more people or maybe robots that could help with that, that would end up providing even more opportunities for that to happen. I don't know about you, but this one is, I guess, on my mind a little bit more these days. You're all getting a little bit older like I am, but basically having some robotic systems to help assist people, take care of things. This is the one that I focus on a lot too, which is, okay, our means of switching production or manufacturing, is quite terrible. If you wanted to make a new electric car, it'll take you 5 years to construct the building and probably another 5 years just to tune all of those robots in the building before you kind of have an okay amount of like manufactured production. If we really have to wait 10 years before we can produce anything in mass that we need, for example, vaccines or anything like that, I'm just not that patient. And I suspect we'll probably it'll be helpful to have a society that can adjust faster than once every 10 years. These days, if we had a 10-year plan, it'll probably be over and useless after 3 or 4 years. So we need to adjust faster. And then way down here at the bottom, and what looks like it was cut off from this figure because I didn't quite look at the details for the slide as much as 11 o'clock last night. But we could be a lot more efficient with space. There's a couple of really nice companies that are using robotics for basically recycling at much more efficient manners. You can use things for like vertical farming. In fact, there's a couple of companies, including like Farm Lever here in Quebec, that does a lot of indoor vertical farming. And if you can figure out how to use robotics in this, you can expand the space for doing more and more vertical farming, which is also really nice because vertical farming doesn't use chemicals, pesticides, a lot of the other things that tend to taint our water supply. And I like drinking fresh water. I don't know if you all like drinking something else, but that's one of my more favorite ones. Okay, these all sound great. And hopefully we want to be able to get much closer to this at some decent pace, not too fast. So then let's ask us the question. All right, what do we need to get there? I put up this picture a bit already, but if we want to make some sort of robotic system that can be more flexible, can be like more adaptable, how are we going to end up making something like this? This is far more complicated than it might seem. I mean, robotics people have been working on this for about 40 or 50 years. But maybe I'll start out. Because this is a research class, so it's definitely going to be a lot more seminar-like, and I'll be doing a lot of discussions. But yeah, what do you think the properties of this agent should actually have? Like, what do you want your robot agent to be able to do?
Understand the context.
Text. Okay. Can you give me a little more context
Yeah.
to understanding the context?
An
example.
It will know which policy is more appropriate depending on the environment of where it is, where the context is. So if there's, I mean, if you have one policy, I think it would be too broad to have you have too many actions in that. So having a better understanding of your environment will let the agent know which action are more appropriate in this one.
Mm-hmm. Yeah. I want to have a better example come to mind, but when you're doing healthcare for people is a little bit different than the way you do healthcare. If you've got like different amounts of resources for those people, you'd probably make different decisions if you had to. Unfortunately, like triage and war happens to come to mind, but hopefully there's a better example out there. Okay. Yes, I mean that's nice. You make these different decisions, and this is even based a little bit off like objectives you want to give to the agent and what they should prioritize given the situation. But okay, great. What else does it need? This is really like a laundry list of tons of stuff that we want our agent to do. You and
be able to cope with open-ended novelty in handling situations it hasn't met before, or dealing with concepts that were not in its training data.
I suppose in this case, though, you probably mean like non-advantageous novelty.
Oh,
Yeah, we probably get into that too, because like some novelty is great. Like, sure, I would really be happy if someone figured out to like process water in a faster way or something, or clean it. That's not bad.
no, yeah. But for example, if you have a generalist robot whose job is to take care of you and handle your tasks, you'd want it to be able to, for example, read the news and it sees that this new water production method is available to consumers, and that it would go, oh, this is a good idea, let's purchase this, and add it to the mix of whatever it's doing for you.
Mm-hmm. Yeah, exactly. Novelty is a really, really tricky one, surprisingly tricky. In fact, in my experience, irritatingly tricky because people do it so well and robots don't. That way. Great. What else does this need?
So look at the point of like reducing the dependence on assumption.
Yes. And I do believe we'll talk about this more too, but these are different. There's kind of a dealing with novelty, being able to cope with it, which is kind of related to dealing with noise and the fact that like variation shouldn't bother you. But then there's going a bit beyond that, where it's like, okay, noise is one thing, but there are, if you put it as sort of like some structure or some component.
I think like reducing the dependence on assumption.
Yes, so I don't want to assume, because that's sort of this example here. It's like, sure, my robot works good here if my assumption is that my world basically never changes and something like that. So we want to have at least less assumptions about world. And by world here, I mean like environment, the thing that it interacts with, and I think there's less assumptions about the algorithm.
And the different modularity, like this,
Okay, good. So that's sort of multimodal is at least the way I think about this, the fact that, if you give me some information, hopefully I should be able to use it. Even though we seem to be extremely dependent on images. And in fact, I don't really know of a robot that bothers figuring out how to smell things in order to get around. But I do think it's chemically possible to do that. Someone has made an apparatus to do it, but no one uses it for robotics. Well, I shouldn't say no one, there'll be a caveat for this entire class. Whenever I said like 0 or none, there's probably one in existence somewhere. So wrong. I think there's some mathematical theorem for that as well. Okay, great. So maybe this is already a short list. It's actually getting a bit long already, but all of these can actually be unpacked a lot. In fact, through the class, we're probably going to have like 2 or 3 lectures on each of these topics and kind of like the ugly details of getting to work. We'll touch on a few of these even today to describe them. One of the things that always ends up being a bit of a challenge too, and we'll talk about it, is sure, we want this big policy. I still want this agent to be able to act in real time. This thing is going to be enormous. And one of the consequences of people using larger models these days is like, I can't wait a second for robotics to make a decision. Say, for example, if you've got like a self-driving car somewhere going through traffic, that might be too late. So all sorts of considerations to think of. But yeah, feel free to like jump into and ask questions, of course, throughout the class, but I'll definitely encourage more and more conversation at certain points. Yeah, so we covered a few of these. Generalization definitely being one, and there's a learning from interaction, which is kind of like a nice principle that tends to save us occasionally. And task and reward specification. And these are like really broad categories that we'll talk about a lot. Okay. So if this symbol here on the left, is, I know this looks kind of human brain-like. Maybe that's an accident. Maybe that's just the way the image generation model seems to like, because most brains are kind of human-looking. But it's the idea, if we want to do generalization these days, we want the scope of this generalization to increase quite a bit, so that it can, like an agent that could still drive a car, a bike. I'm not exactly sure what this one is. Probably a control an arm. And most of these are morphologies and not necessarily different tasks, the way we think about them. But I was giving a little bit of a talk in the RL Sofa for a bit, so I wanted to refine this problem a bit better. But I find that the goal that we should really have when we're trying to maybe learn this, kind of, is really this problem over here. So if we've got any agent, and what we kind of want to do in life is be able to learn as many tasks as possible. Not sure if I can move that up a little higher. Does that at least show up a little bit better? But it's just a grid. We're basically on one side, we've got types of robots, whatever they may be. And on the bottom of this, the other axis is basically tasks. Could be folding laundry, driving a car, whatever. But the goal is basically, we want to get the highest performance across this entire grid while sampling the fewest number of things we can need to from this grid, like the fewest number of tasks, morphologies, etc. And this is somewhat equivalent, basically, where we want to do minimize regret over all possible tasks and morphologies until we can learn a perfectly optimal policy. And it's a big ask that it's never really been done before. But this helps us motivate about why we're making some of the choices. So it's helpful to have generalization across tasks here, which we talked about. It can be helpful from learning from interaction, because maybe there's a whole new morphology in tasks we don't know about. Maybe the system can go collect data there. So we still want to generalize and be sample efficient here quite a bit. That'll help us basically cover this heat map of different tasks and morphologies quite well. Okay, does that make sense? Yeah, it's not totally crazy idea yet. Sorry?
It's already crazy now.
Yeah. It's a big ask. I mean, for some people that have done a bit of robotics before, this side here is kind of doing what Ross has been trying to do for a while, a little bit for both of these. It doesn't really do the learning from interaction part, but it can technically handle different morphologies, different robot arms. It's got different IK libraries for different arms. You don't really need to do much except for describe this is the configuration for the arm. It kind of handles tasks, but not as well. But really the way I tend to think about this sometimes is great. I wants to basically learn ROS. I want to do a little bit better than that, but basically it's this system for being able to control any robot and apply any algorithm for control for it. And if anyone in here has used ROS before and realized how painful it is to like set up and configure, you might also appreciate this goal. Just can we use machine learning to make our software design problem easier as well? Okay, great. So then just really quick notation. Although some of these will kind of transfer back and forth, but this is just, an example of a policy. It's going to take in some, in this case, we'll use images because those are nice and visually representative. And then it has to make some choice between turning right or left. The parameters here basically make up this big giant network of stuff that determines what the inputs and outputs map to. And then we've got actions, continuous actions, states, and observations. And basically the policy is always the same. Just when you see an O inside of a paper, which to be honest isn't always mapped really well in most research papers, it should mean that it's a POM-DP and you don't have enough information to say the state. But I've seen plenty of papers that just use an S there and forget to actually do their notation properly. But that's sort of a different challenge. But the reason for this is because usually we'll talk about two types of problems here. One where we've got basically the entire state. There's nothing more the agent needs to know in order to be able to determine like what state it's in right now. And then we've got observations where there's not enough info here. Technically, you can kind of see the layout through this image, but there's a whole other universe outside of this image. Maybe it's relevant to the task, maybe it's not. You don't know just from this observation. Okay, does that make sense? Okay, great. And then the last part, which makes some of this stuff important, and just being able to talk about what's called the Markov property when you're trying to be able to come up with a policy. Now if we have states and observations, really more in the case where we have states, it means that this state is all the information I need to figure out where I am right now, but it's all the information you should need in order to make the optimal action at this spot. And this becomes really helpful, especially when we talk about items and algorithms that can do different types of generalization later. If you don't have this Markov property, let's just say your life gets much more computationally hard. And if you can figure out how to make things more Markov, it makes your life much easier. Okay. Any questions about Markov, or at least Markov property? I don't know Markov very well. Okay, great. So then basically what we would want is to be able to do deep reinforcement learning. And okay, so there's a couple of ingredients here. We want some system, we talked about generalization, but we also want it to be able to learn on its own, because we'll get to this, but I don't think we want to have to collect all the data for this robot system by hand for ourselves. It's not how I teach all of you. It shouldn't be how we have to teach all of these robots. But basically, it's this kind of simplest structure. We've got images, we've got a deep network model, this kind of simplified version of deep reinforcement learning. The current model spits out some particular torque for controlling how all these joints move for the robot given this image. And then it tries a slightly different torque, and on average, this torque results in a little bit more reward. And then just adjust all the gradients, basically the values of this network, such that the probability of this better action is a little bit higher. And now just do this hundreds of millions of times until you actually we have an agent that can replicate this pretty well. Okay, does that make sense? Okay, then the hard part is, that's great. However, basically this is not generalized scale and needs an enormous amount of data. So on that grid we were talking about of like morphologies and tasks, this basically doesn't fit like any of the stuff that we'd want by default on that grid, even though it tends to like work in practice. Okay. Does that make sense? People kind of familiar a bit with DeepRL? We'll go into a lot more detail about all these things and then like why it doesn't generalize, why it needs boatloads of data in order for it to even get some okay performance. Okay. So basically, thus begins the context of our course. We're going to try and get algorithms like this in order to be able to enable this generalization. Okay. So to start with, And this is where things, we've got terms for these things called generalization, but how well can we actually define them? So we talked about them a bit already, where ML systems, especially robotic systems, they actually need to exist in the real world. And they are extremely susceptible to even small bits of noise. Like if I gave a lot of current robot systems this image and then came in with my really, really great artistic skills and then just put like a dot here on the side of the image for everything that it fed into the policy, it would probably not work anymore, like at all. It probably would work quite terribly, depending on how you ended up training the agent. So this is in some ways very unfortunate, but it's still a bit of like the real case of how things work at the moment. So here, we need to figure out like, okay, we want to train an agent to ignore this, but what do we mean by that? When we talked about being robust to noise, but what does robust to noise mean? And I guess it's really that definition of noise that we need to talk about more. So what do we mean by generalization? Now, this is kind of more of a question for all of us. When someone tells you that, what pops into your mind? Nothing specific? To be honest, I wouldn't be too surprised since generalization is this weird blob where now we want to try and make this more concrete, discuss it more.
Well, let's say you learn to drive on your dad's car, but you're still able to drive other types of car, even though you never drove them. So you generalize driving.
All right, but then, so what do you mean by driving? I could sit in both of these cars and behind the steering wheel and not move. Does that count as driving?
I would say operate the car.
Operate the car. So then what does operate the car mean?
Being able to take action while the car is running, so know when to put the brakes on, put the accelerator, and adjust the steering wheel to where you want to go.
Mm-hmm. Yes, so that's better, good. It's now becoming a little bit more car specific. So now I can only talk about generalization when it comes to cars. I'm not saying that's a bad thing, but the whole point of this little endeavor is that generalization is kind of hard to define.
You're going to do one task, then you are able still to achieve the same task with a good performance, even if it's changed a little bit. The definition of the task, the tools that you have to achieve the task, and change the task.
So then what do you mean by change a little bit? I bet if we all like took like a little, some sort of survey right now, we'd all have a kind of wide distribution about what we mean by change a little bit over task. So is there another comment over here?
I would say unseen task. You learn some task and you can generalize that to unseen task with that.
What is an unseen task?
It was not part of your data set that you used to train
Okay.
the model.
Well, I mean, this, I guess I moved to a different slide. This particular task with a dot here and without a dot. So this one wasn't in the data set. Do you really think, like, shouldn't it should generalize to this one, even if it's unseen, but what really, does this look like something that's like not specifically in the data set? So like, what's your definition of unseen? Like has the exact same pixel values. If you use like np dot all close down to some fault tolerance to like the power of negative like -10, then that's good enough. How do you define that tolerance for like np close? That one's hard. So these are all things where I guess I'm trying to at least encourage in the mind a little bit that like these definitions of like unseen, close, they're actually pretty vague. And we do want to make those a bit more concrete. And mostly because when it comes to stuff in the real world, the definition will really matter a lot. And these days, people are probably going to want some bit more assurances about how this policy works when you say all close. When they say, okay, this works like this, but if a fly comes into your factory and lands over here before it no longer works. We want to be able to say it can ignore these bugs in the environment, not in the code. Well, this is part of what I'm getting to. So it's, you can talk about in and out of distribution. We can go back and forth a lot of what we mean by like close enough, unseen. But a lot of these I wouldn't consider totally in or out of distribution. This kind of goes back to like dealing with noise and other aspects. You could have a dot here. Conceptually, I would suspect a lot of us would call this noise. But then if I came in here and I changed this, it's a puck if you can't quite make out this weird blue blob, so it's a cylinder. If that was red instead, I would think like if I asked it to move the puck to the other side of the table, it should still work. That at least is starting to sound a little bit more like, well, now this is a much more unseen task, not just a noisy example. These are, start to think about this process of what we expect our generalization to be here. And I guess this is good too, because I really want us to set a pretty high bar in terms of what we talk about for generalization. It's the same thing for robustness. People kind of use these terms, generalization, robustness interchangeably, especially when it comes to noise. But robust to what, in what way, and how we can define that ends up being pretty important. And for those that might be a little bit more familiar with, you can have a model that can then have some confidence over its performance here. But what does confidence really mean? Like just because I've been in a state before, doesn't mean that the next state isn't like me getting hit by an asteroid or something like that while I'm sitting in the car. So you want to be able to define in some like relative sense what these terms mean, at least to give some examples of some mathematics, things like that. And I guess I'm harping on this a little bit too, because these days, yeah, every research paper has got some definition. They'll say like it generalizes better and shows a bar plot or something like that. I really want us to think a bit more qualitatively about what they're actually wanting. Like, was it just, look, I added like a weight that's like half a pound to the end of my robot arm and somehow that's generalization? It might kind of be, but we need more information to understand how hard that was to do, or if you've really made much progress. Okay, does that make sense? Yeah. Great, it's sort of the same process too when we go through making a class. If there was an exam for this class, it'd be like, well, I want you to generalize to the new exam, or I can give you the exact same questions beforehand in the exam. And the people that like human beings that figure out how to like generalize to the stuff that was more outside of the distribution are good, right? Or do I give too hard of an exam and like no one does anything at all because it's so out of distribution, doesn't count. So these evaluations are important. Okay. So a lot of these questions are about finding a right representation to begin with. So we could have, obviously we want this to be invariant to things we don't want to care about. Doesn't matter if there's noise, doesn't matter if there's like literal bugs flying inside of the vision for the cameras for the robot. It should be invariant to those things. So start to think about more of those things that you really do want it to be invariant to. And other things that should just be equivariant, which just means if you like filter this through a function, you get some sort of proportional result. So even if you were to change this cat, so you don't change the cat never changed, still the same cat, but you basically moved the camera that you used to take the picture like closer to the cat or further away from the cat. Still the exact same cat. So you should be like invariant to that definition of cat. Other options for this are to be a bit more equivariant. So if you did like the operations to be able to compute the output for some function, you can do them in different orders. Still ends up having the same result, some sort of proportional change. And a lot of what we're going to talk about is these are starting to have some properties that give us that generalization we want to talk about. But now we need to be invariant to some things we care about and some things we don't. So different cars in or out of distribution for something. And we'll need to talk about this distribution. And then when we talk about relaxing the most amount of assumptions, it's basically, I want to be invariant to the largest distribution of stuff that shouldn't really matter what you're trying to perform. Like right now, I'm teaching this class. I'm trying really hard to not care about the weather outside. It doesn't really matter, except for like the first joke inside of the class, besides that as an informative notes.
Yeah, who's the we in the we should not care about?
All right, where's the we on this slide? Okay, so we, yes. So it's a good question. I mean, in this case, I use we as we, the researchers, but you can also think of this as the agent. We constructing the agent, we want this agent to be invariant to something about the system such that it can generalize well, such that it won't be so susceptible to noise and variation.
This makes it sound like there's no like, you have difficulty formalizing a notion of generalization that doesn't have some sort of observer dependence.
Yes.
Like, it depends who's looking at the system, city.
So yes, that's definitely very true. So you do want to talk about like invariant of things that the agent could not care about in order to be able to optimize some rule or function. Would be at least a little bit more grounded to talk about. In practice, though, I'll just say the observer exists in every research paper because there's some motivation to make sure your method works better than the firework. So that's why you might pick the invariances that you care about for the agent in your paper, dependent on the applications that you have. So you'll have some subset. So even though there are a lot of papers that say like general purpose robotics agents, a lot of them are targeting like at-home cooking and cleaning tasks, and maybe those aren't the ones they care about. Or some other group of people care about. And it's entirely possible those algorithms will now be biased to working well inside of what seems like San Francisco-based kitchens, maybe not other kitchens around the world. So that was important. So then this is all about, all right, how can we achieve this? Okay. So one way to think of this is, so we want to be able to have this, we'll talk about like one type of invariance right now. Because a lot of this is, sure, we want things to be invariant. One way to think about this is how to, like maybe we can achieve this by figuring out how to reuse data really well. It's something that people do kind of irritatingly well because like think of some examples. How often do you reuse some of your experience? Probably like every day. Do you think you reuse something that you've learned from before? Yeah. Like how many of you got to this class? I don't think you learned entirely from scratch how to like leave the front door of your apartment or house for that day in order to start getting here. So that was even your first step. You probably reused a lot of steps until you got here. We all generalized really well because it's far more snowy here than it was the last time I was here in December. So we're even doing some visual generalization there. But it's because we're reusing a lot of data. We're surprisingly good at being able to do this, and our algorithms are not fantastic. I mean, we do want to relax a lot of assumptions, but maybe we also might want a few like priors in the way that we're constructing these models such that maybe they're good enough assumptions for now in order to do this. So this is really where if we can achieve this really well, part of getting this data reuse is kind of like an implicit condition to getting very good invariances. That means that I can, if you can reuse your data you've collected across more space, it means that the information in that data is more invariant for other things, which means that like the robot in that desk, if you can reuse data well for being able to move around objects like that puck, then it means, okay, if we can transfer information to this giant Lego block or what I think is a red towel about how to manipulate objects and reusing information there well. And it has invariant or at least more invariant model for how the dynamics of the world work.
Equivalent to reuse the data.
Yes. So here, this is like a robotics and more like RL class. So we'll talk about experience, but we can use the term like information, data, and experience kind of interchangeably, depending on what like textbook you're reading at the time or looking at. But like data is just, here's the collection of experience so far. Inside of that data and experience is at least what I call more so information. There's something in there that we can hopefully reuse and learn from. Okay, does that make sense? Everyone's really excited about reusing information. It's basically the act of being a researcher and doing science is you will take a collection of data that looks like a blob of junk and you try to distill it down into a couple of rules and facts that you can reuse. So you're trying to come up with the most reusable chunk of information that you can use from this. So we're trying to make robotic scientists in some way in order to be able to do this. I like giving this example because it's a much more clear one. So we want to reuse stuff. A lot of this comes from learning different types of structure and being able to do this in more and more clever ways. And then here is sort of just an example of this, which I mean, we maybe all experienced today, more or less, where we could have a bunch of sets of experience where we traveled different trajectories to get to different locations. But now we want to go, you know, from, what is it, like the red house in order to get to the beach. We've never explicitly traveled along that exact trajectory from before, but we should be able to piece together our trajectories of experience that we've used from before this. And because of that, we're really good at being able to do this. We, in this case, being human beings, but learning agents are not fantastic about being able to piece this together. In fact, they're quite terrible at it. And this is a really open research question. If an agent is given a giant blob of data of trajectories that travel like all over Montreal, and doesn't have to cover literally starting from every position and going to every other position, because that would be a huge waste of data. How can you, from this, basically construct an agent that can now go from any position to any other position? This is kind of a version of that grid before that was any task on the left and any other task at the right, where now you've got one starting position and one end position. And we want to sample travel at least that we have to across Montreal in order to piece together that navigation grid. And this comes, well, at least on Google Maps, you know, this comes because we've got the assumption that at any like transition point across two roads, you can go right, left, or turn around there. But that becomes, that's kind of an assumption because of what we know about driving and biking. It's harder to bend and understand the truth of this if we think of just any type of like planning data collection problem. Where if I gave us, you know, just a bunch of trajectories of a robot or moving around trying to manipulate objects, it's not quite easy to see where these trajectories properly overlap, and then you can piece them together. So it's nice and easy here to visualize. Okay, any other questions? No? Good so far? No? Okay. All right. So then that was being about one way to be able to compose literal data together, such that you can construct a model out of that. Because a lot of what we still want from this is being able to get composition. So we could learn one policy. Let's say we want to do this driving policy that now goes from your home to this particular classroom. And this is going to be a pretty long horizon for the most part, makes planning very difficult. And just think about the process. If you tried to learn this, you'd start from your home, you'd sample trajectories randomly. The probability of you accidentally ending up here in this room, really, really low. So it'll take a really long time to do this. And there's going to be a lot of complex credit assignment issues to see, okay, no, this particular trajectory was slightly better than this other one, to figure out how to make small improvements on this model. So basically, should we break up, one way to compensate for this is should we break up this problem into other pieces? And I don't know, how many here cook? It doesn't even have to be regularly. You've cooked a few times in your life, right? Okay, but there's probably a lot of repetitive things that you do when you cook. And a lot of things that are technically compositional throughout that. So if I was to cook soup, I'll use I in this case because I cooked soup last night, so it's pretty fresh in the memory. But like the first thing you do is you got to use your task, basically like fetch, grab all the vegetables and items that you probably need. You've got to cut some vegetable some at a time, so you got to cut a few different onions. And then you get down to this motion where you're just chopping stuff. And that is going to be a pretty repetitive motion where you don't really need to construct a policy to include every step of being able to chop a particular onion. Can you piece apart this particular chunk of doing a particular chop such that you can just do like chopping motion? And now that's one policy, and that doesn't need to change much. And now we can hopefully have this policy that then becomes reusable. The nice part about this, if we do this really well, is that chopping motion should be invariant to whether or not, I don't know, it's later in the day, whether or not there's snow outside or not, although that might determine the particular kind of soup that you're making, depending on how cold outside it is. But you mostly get to this point where, like, well, now you can see that there's at least small motions that you can kind of perfect and be able to reuse. This chopping motion will probably, the number of chops you have to do might change a little bit per vegetable. Technically, you can use a lot of similar chopping motions across different vegetables. So you can start to reuse some of the information that you've figured out so far for being able to chop vegetables for other vegetables. Such that really, it's not one big giant long sequence. Technically, we're piecing together what could be like 5 or 6 unique policies here. And then from that, where we can start to get some of these invariances, some of these better parts of generalizations, if we learn these policies well enough, then by default they become invariant, because they're invariant to types of vegetables. They're invariant to how long that vegetable is. If you've ever cut in a carrot, these days they're enormous, so they can take quite a long time to cut. But this is one way, just even looking at one single planning problem. If you start to chop this up into smaller policies, every one of these smaller policies has 2 features. One is that it does operate over like a limited time horizon, so we know we can kind of piece that together there and make some smaller, more robust policy. They usually also involve some amount of information hiding. So like the particular policy I may use to cut vegetables doesn't care about a lot of the other stuff that's going on in the world at the time. And you literally don't even need to include it in the training process. So this concept of information hiding usually means that you can have a lot of like, you can ignore a lot of variance, or sorry, a lot of noise. And because of this, you can construct a more invariant policy. It's hard to learn this entire thing from scratch, but at least you start to get the idea. Okay, right? Yeah,
I don't know much about RL, but in machine learning setup, you can think of building a lot of classifiers, representing classification, and so on and so forth. And then you have a lot of classifiers. And then you could say that we are hiding information there. But we don't do that anymore. These days, it's language models. One model can do all of them. Let's say multi-assignment setup. Why don't we motivate from there? We want to do that. Not learn just little policies.
You mean like, why do we motivate that? Why wouldn't we want this from language models? Or why
No, why
wouldn't
wouldn't we think the same way for robots and policies?
we?
Why you want this small policy by specific?
Well, for one thing, it's not entirely impossible that language models are essentially learning a bunch of this. There's people also writing a couple of papers that say there's a lot of like programming pathways inside of my language model that only activate certain chunks. So essentially, that might be one giant like hash function that just goes into, okay, someone's given me this paragraph. Now I'll activate this particular chunk of my network that is essentially a little sub policy inside of it. That says, okay, now this part of my chunk of my network handles all like recipe related questions. So there may be a lot of sub policy information in there. But the point of, I guess, in the relation here to connecting these is it's nice mathematically because you can show and say that these policies can have some variances. But it would still be nice to learn this entirely in end-to-end fashion. Because I mean, if I was to hope to do this, and this is what people have actually been trying to do for a while, robotics has tons and tons of hierarchical policies. But there's always some brittle points where you try to connect these policies together where it doesn't work as well. So we do, in many ways, want to make one giant model that would handle all of it. But inside of it, we still want reuse across these different models. And a bit of the work I do is figuring out how to do some stuff related to routing networks and figuring out if there is these more modular components inside of the network. And then I know they can generalize better to random inputs that people might give to my language model. Does that make sense?
Yeah.
Okay. Great. Other questions? Okay. So then a bit conceptually, so this is where these two ideas kind of come together. So you could do this, where if we had a big set of policies for each task, it gets a bit ugly, a bit unwieldy. And I guess I've sort of already given away a little bit of the punchline here. But if you have policies that work for like every single different onion, then you start to end up with this kind of bad situation, right? Can anyone guess why we don't really want a unique policy for every task?
Too many balls.
Yeah, at the very least, this will be the least memory efficient thing you could do on your computer. But But it comes back to what we were talking about. It's like, we really want reuse. Like, I want one model that does blend all of these together, makes good use of memory parameters, still generalize as well. But at the moment, we don't even get any reuse across this. And it becomes very tricky to be able to use. Even if there is a lot of similar structure across these. For example, like you mentioned the LLM example, but for most of these policies, they're gonna have to identify, like, have some visual perception system. So I would think for like the top 4 of these, just being able to perceive items in the world is something they will all need. But I would really hope we can share that visual perception pipeline for all of these policies together, at the very least. The rest of the stuff might be a bit more specific because we're all, I don't know, slightly taller and faster in our arms, which means we might have to adjust our policies a little bit. Okay. Does that make sense? Here, before we were talking about data reuse and literally trying to get the most out of it. Now this is, to do that, we can start to get a lot of, even implicit policy reuse starts to be a good start. But maybe as a part of, like, a bit of a reminder is that, yeah, we're going to talk about using different types of generalization and large models and things in the class. We still need some fundamental principles to talk about, so that we're not just saying like bigger model, more data means something. In fact, one of the big questions right now in the robotics community is how do we know when we have enough data? Because it's literally, it's not the language model case where we think maybe we have enough text to describe everything. Now companies are paying lots and lots of money to generate data, and they want to know what's going to be the budget for collecting all this data. When can they stop? When do they know they need to collect more? And unless we kind of figure out this process more, we might, I usually think in time, we're going to waste a lot of time collecting data we don't need, unless we can figure out how to do kind of reuse really well. Okay. So instead of having this set of policies, I was going to give this smaller example. You could create one policy with basically just this nice context variable. This can work really well, so at least we can index into things. So we could have one that says like the chopping policy, and then it works for onions and carrots and celery and what other vegetables actually exist in the world. And then you can have this policy that works for being able to do all these cuts. It does get some generalization from perception, but we end up having this pretty ugly, it's not ugly, it's just hard to figure out how to use this one hot vector. So that if someone asked, we wanted to use this policy to generalize to a new vegetable, how do we get this generalization to work here? We probably have to figure out, okay, what's the most similar vegetable and try to give it the same context. I'll just say I'm too lazy to be able to do this, and I want some automated system to figure it out. So here, instead of using basically a 1 at some specific index, can we do better than using these one hot encodings? Okay, let's pause there for now. And it's been 50 minutes, we can stretch a little bit. And then I'll start back up again at what is 2:30, 2:31. Okay.
I have a small question.
Sure.
So in this table, I'm finding it hard to understand how this robot can assemble. So I think we mentioned how each of the grid points is important, and we need to
Mhm.
able to arrive at that.
So two things. I mean, a robot, even like the Boston Dynamics spot robot with an arm on it, it could assemble some things. Like if you gave it like one of those kids' toys that's like to put like the puzzle pieces together, it can. It's not fantastic at it.
Right.
I mean, I will state that point, but I think your main point is more important, where not all robots can do all tasks.
Hmm.
And some of them are even designed specifically to solve certain
Yeah.
tasks. So it's not that it may be impossible to collect data for some of these,
Hmm.
in particular, like combinations. But it would be, I'd hope that if the collecting data somewhere else would help it still give it some information about the other tasks and how to generalize.
Yeah.
So that part is one of the trickier challenges with
Mm.
understanding how to use all of these models. But yeah, we'll get to more details on that at some point. In fact, I've got a slide on that in a couple of slides.
Got it.
Yeah.
One other thing, what do we exactly mean by morph and morphology here?
So it's literally the robot's design. So like, what is it? Like, how many legs or arms does it have? How big or small is it? Yeah, it's also, other terms for this are morphology, embodiment, design, I guess it's configuration, but they all just mean like, what is its physical being
They
that
come in
allows it to do stuff?
very many shapes and sizes. So what does it exactly have is what you said.
Yeah, which can, yeah, I guess we'll stick with that for now. That actually gets really complicated the more and more you think about it. It's like literally when you're running a robot and it's battery powered, technically it loses a little bit of weight as it discharges the battery. It's like minuscule, but it happens.
Yeah.
But we don't really talk, that's not as important. But yeah, dealing with the embodiment in the agent is complicated.
Right.
Yeah, but makes things interesting.
Got it. Thanks.
Sure.
Mhm.
All right, everybody, let's get started again. The little break. Okay, so I traveled through a wormhole to slightly later in the slides just to make sure we get to cover this. And then I'll go back to like the research topics for the class again. But this is just a little bit on the course in case anyone has questions. So it's just the goals. Basically, the goal of this is to be skilled enough to do any of like good and in these days, which is going to be more scalable DeepRL and robotics research. So that's kind of the output goal. This means learning a lot of kind of unwieldy and complicated tools in order to be able to get there, because that's just the fun stuff that's getting it done lately. So a lot about deep learning, a lot about reinforcement learning, a lot about generalization, a lot about large models. Probably not enough time for safe RL, things that are more along the lines of offline RL, using things like transformers, and we'll talk a lot about using. There's some real magic these days going on for using like VLAs and creating those. So there seems to be a new one every few weeks, but some topics related to that as well. So we'll cover a lot of that. A lot of this is to learn how to think about and participate in this research because it's incredibly fast, the way that it moves these days. Of course, having some fun, because otherwise why do it? And then, figuring out to do some more learning, work on projects, discuss the problems. Like you should definitely get into this course, like what are the current, most interesting and complex problems that are holding back the ability for us to be able to make agents that work and generalize well in the real world. And what causes them to not be able to do as well as we would hope. and why new algorithms and models that people are using address some of these problems, but not others. There'll be a couple of homeworks for the class in order to get some people some experience for this. There'll be some like behavior cloning, and then we'll do some like larger models for behavior cloning. DQN, so at least some off policy RL algorithm, because that's the more popular stuff, but scaling okay. And then this, with any luck, we'll be able to deploy this on the couple of legged robots that I've got in the lab, so you can see how well your deploy policy works. We'll see, we're still trying to get the calibration to work properly on that robot. This one, definitely some offline reinforcement learning, which also has been working pretty good for scaling up and working for large models. And this is where more of the vision will come in. We'll try and deploy on a couple of Viper X arms. They're also in the lab. You can also use either of these for any of the projects that you want to do in the class. We've got, I think, 3 of the quadrupeds and now like 8 technically of the robot arms on the bottom. So we'll figure out how to share those. And the last part, as we kind of cover all this stuff, to be honest, I find this is the easy stuff, or like where I think scale will probably work okay, and down here when we get to the deep reinforcement learning. Scale is being really, really painful in order to get working. So a little bit about scaling up DeepRL algorithms. Basically, how to struggle our way through this, because we have to deal with basically doing a continual online learning problem while trying to mess with a big model. And these things just don't like each other. And there's some new methods to be able to improve on those a bit. Yes.
What do you mean by scaling? You mean more agents, more?
In this case, I mean deeper networks. So something like we'll probably do like a basic network, a ResNet, and then one of the like vision transformer models that I've not prepared. And then I'll see that like some of these are going to work. And to be honest, like the end of this assignment is almost like it's a research problem. Like you're not going to do well on part C of this assignment, but at least you get to understand how painful this is. If you've got some ideas, great, run with them. Let me know how they go in the future. But a lot of these assignments now are actually going to be, and this is as good as large scale DC works right now. If you want to do better, good luck. It's a research problem. And same thing here. You want to deploy this stuff. You want to try a big model and have it deploy in this robot. You know what? It's not actually going to work that well because you're going to get time delays and it's going to stop functioning in real time and you're going to run into issues. That's a research problem. So there'll be kind of like 2 questions that are, we've done these ones already, we know what work, just so that your algorithm is functioning. And then when you try to scale this up, everything starts to break. And then you'll start to see where the cracks appear and then where you can go off and do some more research if you want to figure those out. Same thing for offline RL, which is trying to do some of that stitching stuff we did from before and generalize well from offline data. It's actually not fantastic at this, and you probably need to improve those algorithms. And the last one I already mentioned. Besides that, I'm trying to scale down these homework assignments a little bit so they're not too much work. That being said, because this is more of a research class than a seminar, and my plan is to basically stop, with the exception of today, in like the last half an hour to 20 minutes, and we'll just take up talking about like, what did we like or not about the papers that were assigned this week for reading, or like bring them up. So like there was a ton of papers for today. The idea is you just kind of like pick one of them, write a short summary on like why you thought this was interesting, what was interesting about it, why you think it's good or bad. That's it. And this helps, one, give you some practice for writing a review for a paper, which is good. It also gives you some practice for this because basically the only way you can judge your own work is acting as a reviewer and thinking, okay, what would my or someone else in this class criticize this work for, and then maybe I should adjust it a little bit. Do make note though, okay, the LLM use on this is going to be somewhat strict. So like, don't just send me an LLM generated summary of the paper. I can promise you I did that already this week and I graded all those papers, got a D basically for those summaries. So add a little bit more information, at least to this. It should be your own ideas and thoughts about the paper. In fact, it's pretty easy to use LM stuff. So I'm probably just going to feed it through a couple of different LMs, generate the summaries, and that'll be me in the class. So if your summary matches that one, not going to be good for you. And Gradescope is great at identifying the similarity between different summaries. And besides, if you kind of skip this, you're kind of just saying you're not interested in trying to think critically about your research. You don't have a good plan. It's like I said, it's a very important skill, because what you can't explain, even if you didn't do it with someone else's work, you don't understand, so it's really working on the critical thought process for research in this area. And then maybe knowing how to solve every problem that has ever been solved, hard thing to be able to do, sort of not the point. Okay, does that make sense? I'll go over some of these summaries. It becomes helpful too, because at the very end of the class, we'll basically provide feedback to each other. So I'll grade everyone's summaries, so you get good at giving summaries, and then everyone's projects, you'll be able to provide feedback on each other really well. Okay. Midterm. I don't think I'm going to give a midterm this year. Mostly, I don't have time to grade it. And I've got some other ideas besides that. So instead, basically a large portion of this class is now the project. So that means there'll probably be a few extra steps for the projects. And the project is basically splitting into groups of about 2, coming up with an idea you're excited about. It should use some stuff that we're going to talk about in the class. That's really my only constraint. And then we'll just go through, like every couple of weeks, there'll be like an update on the projects. Or we kind of basically are writing a report for the projects. Every 2 weeks, we'll like write the introduction, write the related work, and then we'll go back and forth on that for a while. And a couple of other steps. Besides that, like I said, there's some hardware available. Some of you really want to use hardware for the project. I encourage it, because you'll learn more about the actual details of what works and what doesn't for some of these models. And then at the very end, yeah, we'll basically get into a group, we'll present all these projects. We get to kind of commiserate over how painful it was to get hardware working, or how things just didn't scale as well as we had planned, or maybe, and of course, some things will work, some things won't. Does that make sense? Any questions about the project?
Are we allowed to use our own hardware?
Sure. Yeah, you don't have to use the stuff in the class. We've just got some budget to buy a bunch of those arms, and then we're also using those for the homework assignments, so they're set up. But if you have your own, go ahead. Yeah. Yes.
When you say real hardware, is it included computing hardware? No, I mean robotic hardware.
I have for this class before made special requests for Compute Canada to get like GPU hours. So yeah, send me a message on Discord. So we used to communicate, and I'll contact them again tonight about seeing what I can get for this class. But this is mostly physical hardware, at least that was provided by only me. But the compute, I can usually do a little bit about. Yeah, that part is trickier. Okay. Other questions? No? All right. And then just, oh yeah, this is now 6%. Yeah, some of these numbers slightly subject to change depending on my and your situation. But there's like some class participation. Like I said, answering questions, we're literally going to discuss some of the research concepts in this class and why they work or don't work. So you should be excited to come into the class. Partly because we'll talk about some of those papers to review too, and like why we thought they were good or bad. Or like why we thought one of these 3 papers tends to stand out over the other ones. Doesn't mean you have to read all of these. I, of course, will encourage you and say to get a full experience for everything in this area, you should probably read every single one of those papers, but you don't have to do it all right now. Depending on what your bandwidth is these days. But mostly I'm just saying to get up to this is, all right, we want to do this well, and we want to be good learning agents. And an agent that learns really well has to make interventions into its world. And this is partly a DeepRL class. And that means asking questions. That means answering questions and thinking about things. So if you don't ask any questions in this class, and we'll talk about it, it's theoretically like almost impossible to learn the concepts of this class if you don't get into it and ask questions about it. You can't always passively learn every single thing in existence to be able to understand what's going on. I also use this principle as well. So I'm going to ask you questions and give you written stuff. I need to do my own intervention to see whether or not your causal model lines up with the community's causal model for how robotics works. Okay, does that make sense? Ask questions, get involved. Not too hard to do. Great. And then here's just a bunch of links at the end. There's a course web page, which I think I shared in the email that 28 of you should have gotten already, but now there's like 34 or 35 people in the class since last night. We're not going to use Studium at all. We'll use Gradescope, makes my life easier, and we will all chat on Discord. It's much faster, more flexible. You can always include videos and stuff. Okay, any questions?
For the grade scope, I think we have not received it yet, so.
I'll probably just resend another email out. It's like, that probably just happens where you either missed. So I added a bunch of people to Gradescope on Sunday. Maybe it's possible you missed that email. Otherwise, there are more people that joined, and I will do this again today or tomorrow to add people on Gradescope. Yeah. All right. All right.
Write summaries in English or show it from?
You know what? Yeah, you can write them in French. We'll see how that goes. I can read French, but my spoken grammar in French is not fantastic yet. Yeah. All right, cool. All right, so now we're just going to kind of rewind back to whatever slide we were on. Wow, that's a bit of annoying. All right, we were right about here. All right, so we were talking about, can we do better than one-hot encoding? And then people are probably a bit familiar with how we can do better than this. So one example of this is a nice paper that was one of the first kind of larger scale behavior cloning papers. So rather than using a one-hot encoding, you could use text, you know, like, please fold my laundry, rather than figuring out how to do some really complicated math to express how to do this inside of a bunch of one-hot encodings. Where basically the goal is, well, now we've got some model. And we just train a deep network model, takes in a bunch of images, takes in a bunch of, you know, text-based descriptions of how to do what the goal is for those goals. And then train the agent to be able to solve those goals. Basically, this is behavior cloning though. So this sounds nice, it's not so autonomous. So we need to first ask a person to go and collect that data. And here's the goal for it to solve. Essentially control that robot arm, maybe via teleoperation, to go and do that task. And then someone just writes up hundreds and hundreds of these tasks, asks another team of people to go and collect data controlling this robot arm to be able to solve all those tasks. And then, you know, the goal is hopefully train this agent over all that pile of data, and hopefully it'll generalize to some of the text slightly outside of what was in the pile of data it was trained on. And this does a little bit more than that, at least if you go and read this paper. I have a nice new one where it does try to connect a video and language all together. So maybe you don't have a lot of text descriptions of all of the different things that an agent could do. You can try and align the video description and the text description together. So you've got one representation to describe the goal. Way better representation than that just one hot context vector. And then from this, now you can specify a video to describe what you want the agent to solve, or a piece of text to describe what you want the agent to solve. Okay, does that make sense? So it's already a beginning. I mean, it's not easy to train this particular representation where text and video perfectly aligning. Some might know. It's even hard to collect this data. Like if I showed everyone a video of a robot doing something in this class, I would bet a lot of you would describe it differently. I don't even know if any of you would write the exact same sentence of what's going on. So there's always a little bit of ambiguity we'll be dealing with when we use those types of models. In robotics, we tend to like start a little bit from the high ground where we want the data to be like perfect. So we usually start out with the sentence and then go and tell someone to collect a robot video of describing that sentence. And then there'll be some prop or something around it that says, no, that video was not accurate enough to describe that sentence, and we'll clean the data very carefully. Just because in our models, they do tend to be more susceptible to noise. Maybe it's because of a lack of huge piles of data at the moment, but it's something we'll be able to talk about. Okay. So this results in, you know, some work. All right, cool, that function. Where now you can just feed in, you know, place the banana in the purple bowl. Okay, this is probably placed the bottle in the tray, or I probably grabbed the wrong video. Trust me, these were supposed to. Maybe the other video works properly. Nope. All right. All of our machine learning stuff has still not solved the problem of me sticking videos inside of a PDF file. even though I spent a couple of hours on it. But basically, now we can provide just nice text-based goals. And one of the reasons why I like this more for this representation. All right, now everything's broken. Technology. Not again. I think I can go back in the history for this really quick. Hmm. Okay. And I guess I will use the version that you all have. It's probably easy enough for technology right now. Teaching robot learning. Okay. I'll be a little bit more careful about sticking videos inside of PDF files, I suppose. Okay, so those were the results that were used. This is nice because you can basically construct a model that can condition on text. One of the reasons I also like these models a little bit more is, I mean, using text is nice and easy. It's easy just to type up something and ask some models to be able to do that. If you had to create a video of the basically task you want the agent to solve, that's a lot of work. And we'll talk about this a bit in the class too. Like, if we're going to be collecting data that we're going to be training models on for these robots, we do want it to be probably like easier ways to collect data. Making a video, I don't know if any of you have tried to make like a video you put on YouTube or something like that. You probably put a fair bit of effort into it, some editing, a whole bunch of stuff. It's really hard to get it perfect on the first try, something like that. So that's why it's nice to be able to start with text. Also, if you do it really good, it means you never actually need to solve the task in the first place. So if you have to give a video of like the robot learning to fold laundry or like cleaning your room, this means your room needs to have existed in a clean state at some point in the universe. But if you can just use text, it may never have had to actually achieve that state in the data set, but you do at least can describe it. Okay. You can do some more. There's been a couple, to be honest, many papers like this over the last little while, where you could do a couple of other problems, and you can train a couple of policies that'll now use a combination of things. There's some more details in this paper, but basically you can train a model that kind of tells the robot about what it can perform and how well it is at performing things. And then when you ask a task of it, it'll kind of do a little bit of a multiplication of, okay, here's a plan to maybe try and solve that text-based task, but actually I'm only good in this area of the state space, so it'll kind of steer the robot towards what it's still good at, even when it tries to solve that task. So you're kind of weighting this by something that says it's good or bad at certain things. Okay, so this is great. The text conditioning can work well. In a lot of the examples we'll start out talking about in the class, the text variation is not going to be huge. It's going to kind of just be goals by text. And then later we'll talk about trying to essentially glue these models together, take advantage of other models that are trained over larger amounts of text. But it provides a good goal representation. Pretty easy to describe, somewhat, make my room clean, although there can be some challenges there. The problem is this often underspecifies the goal. If I told you to, I don't know, fold the laundry, I would bet we would all fold the laundry to slightly different extents, or we'd probably fold laundry differently inside this room too. So actually, we're not specifying the task, in some cases enough, at least for me, and like maybe my mother-in-law or something like that. They've got pretty high expectations for how things should be folded very carefully. And if you don't do it their way, you're not solving the task. And somehow there's some implicit context there that says, well, no, you know what I meant. But no, that doesn't actually happen. So we need to be a bit careful, especially when we're talking about generalization. When we write in some particular task and we underspecify it, there are lots of ways to seemingly solve that, but it's not actually solved the way the original person intended. So we should probably at least be either providing more of this context to make sure it's solved how we want it to be, or have a better definition for what we mean by satisfying that goal. Otherwise, we might just be pretending that it did actually do what we wanted to do, or it was close enough when we're not really setting good expectations for the agent. There's also a lot of limitations, like even if we just want to use text, these days there's a lot of challenges for figuring out, all right, is there any grounding in the model? Which we'll talk about this a lot in class. If we really want to shine a light on terms that I think are not well defined in our community, grounding is definitely one of them, even more so than generalization. But the idea, or at least the concept is here is, you know, like an orange or a cup is not just like a token inside of embedding somewhere. It's a physical object that you use for things. And if you want to have it understand this item and maybe generalize the different aspects for it, it needs more than a token association. It needs like a contextualization of what it's useful for in the real world. And this helps, the text might help with some purpose, but we really want to understand the dynamics. Otherwise, it's really hard to like make tools and generalize them. And the agents sometimes need to learn to interact with these symbols, and there's different ways to be able to combine inputs. So, how do I put this? So images can be needed to solve some closed loop manipulation tasks. It's really hard to describe, you know, a table layout and moving objects around in just text. Much easier to use an image. So we will get a bit used to when it's better to use different modalities of data to describe what's going on. Sometimes they're better for goals, sometimes they're better for saving information. So we'll talk about a couple of different multimodal models. That's one of the reasons that some of these like larger models are becoming more and more useful, or like solve a couple of the problems in robotics, is because I want to be able to use like whatever sensor I have on the robot, not just images. So we don't want it to just be a model that's been kind of prescripted and designed for things that only work for images. Because what if we want to give it LiDAR sensors of how the room looks? Maybe we have a robot that can smell, and its job is like to detect fire or something like that in the building. So having some large multimodal system gives us more abilities to give the robot information that it can use to make better decisions. Okay, does that make sense? There's kind of like 4 different topics on this slide. And every like 2 or 3 slides is going to be a whole lecture in this class, basically, to dig into these details. Okay. So let's talk a little bit about data. So one of the keynote talks that was at NeurIPS this year was Ilya, who is, to his own defense, he's not a robotics person, so he probably wouldn't think about this very much. But one of the claims that he made in this talk, well, that is far blurrier than I thought it was going to be. Hopefully that's at least a little bit better. If you can see this part that I can kind of highlight, he mentioned that data is not growing. By this, he really meant that text data, like all the stuff that's on the internet, we're not really adding a lot to that proportion of data as much as we would think. So there's kind of like a limited amount of stuff we can actually start to learn from. If you want to know the truth of the matter, actually the language models are being trained on less and less data because they're being sued for copyright infringement more and more often. So actually things are being pulled out of data sets. So it's not even that data has stopped, it is reducing. Now they need to somehow improve their model performance as they slowly get more and more data removed. But I have some good news. They're hiring tons and tons of PhD students to basically rewrite textbooks and include that data back into their data sets. So that's a possible job in the near future, but it means you should probably be good at doing your paper summaries because that's what they'll be looking for. Okay, on the bright side, robotics people were probably a little bit baffled by this because we are not running out of data. The sheer amount of video and robotics data we could collect in any day is amazing. We're just not entirely sure how to best use it yet. We could use it to collect some models. We're kind of getting at the cusp of being able to train good video-based models, but they're still really tricky to get working right. But really, we're not running out of data at all, especially in the robotics context. I don't know, I think I have a slide on it here too. Technically, there are about 2 to 300 million robots in operation right now today, depending on how you define them. I mean, there's self-driving cars, there's a ton of different drones, there's all sorts of manufacturing robots, seemingly making huge amounts of data. The caveat is no one likes to share their data. So now we have tons and tons of siloed data. If I could do something about that, I do wonder how much progress I'd make in like 6 months if everyone just shared their data on that particular problem. But I'll worry about that in the future. So this is a little bit about, there's actually a lot of data, still a lot of stuff that we can generate. There's different ways to be able to generate that data, and we'll talk about that a fair bit in the class. Often what people have done in the robotics community is a form of teleoperation. Originally, it meant literally, you'd like turn the robot arm on and you would grab onto the robot's arm and then you'd move it to where you want it to go next. And you push a button, say that's the key point, and you move it to where you want it to go again, you push another button and you record that data. Thankfully, we're really not doing that much anymore because it's really slow, but it worked for a couple of decades. These days, telling up data, I think I meant to put a video in here, is 2 things, either like using like a VR head, like control system. And then basically when that person moves that VR system, so does the robot move, almost mirroring the person. Even more advanced systems actually create like an entire VR suit. I don't know if any of you have seen any of these at like the Figure or like Optimus Robotics companies, but they're all really fixated on humanoid robotics. So it's easy to just kind of like take a human being and strap a whole bunch of instruments all over them and sensors and then record what they do in their tasks and then use that for behavior cloning for humanoid robotics. And a lot of people are betting on the fact that they think that'll work out well and we can just collect large amounts of data from people. We'll see how that works. The other one that's a little bit more flexible and it's not really in this particular setup is basically just like 3rd-person data people. Like how many people, like, I don't know if you remember this from when you were young, but like watch your older sibling or your parents do something and then try to repeat what they did. They didn't tell you how they moved their muscles to do that stuff. You just watched it happen. And then you had to like translate that onto yourself. And there's a lot of people working in that problem. It's a little bit more unstructured. And we don't even technically know if there is a mapping from that person to you. Like, and maybe there's probably plenty of examples how like one of your parents, I don't know, picks up like a 50-pound bag of flour. That's not technically something you can replicate, at least at a really young age. So there's going to be some physical constraints that may not even be realizable. That's why people really like, at least the robotics people have started out with this teleoperation, because we know what we want the robot to do is already physically realizable by the robot, where it's kind of controlling it to do stuff. When we get kind of further down this, like I don't know if the robot can even do what I can do. So I might be asking it to do something mathematically and dynamically infeasible, even though I really wanted to do that thing. Okay, does that make sense? A lot of complexities here. Any questions? Good. Okay. Okay, but this obviously will help lead into the next context is, oh, and this is, all right, I want to talk about this point. It's really what we're trying to do in terms of machine learning these days. We want a whole bunch of data. We talked a little bit about when do we think we'll have enough data, but really an agent needs to get to this point in its existence after collecting enough data that it experiences enough diversity to realize there is really no diversity. Okay. Does anyone want to guess at what I mean by this comment? You have to be critical. Go ahead.
So we can generalize.
I mean, it does help with the generalization for sure. But can you like unpack that a little bit more about why does this start to get to generalization?
The task itself is the same, the context is just a little bit different.
Yeah. So if you're talking about the task here it's talking about the amount of data diversity that you want something to experience. I think overall you're on the right track. There's just something about. There's like a uniqueness that doesn't actually exist, that only after you experience enough data, you realize that there's not actually that many unique things out there. If that helps. So like if you were trying to specify things in text, like having a robot go and, I don't know, close a laptop in this room or something like that, it can now pick any one of them, but only understand what a laptop is after it's seen like 100 different versions of this. And at some point, it's actually, there isn't, millions of different combinations of pixels and rooms and computers. And now actually, it's effectively, we kind of like reduce the cardinality of the universe after we've seen enough diversity to really understand, okay, no, these objects are actually, when someone talks about it, they mean this class of objects, like this distribution of objects, and just treat that as one item almost. And we were maybe getting to some of those concepts with enough data for language models, but in terms of robotics models and video data, I doubt we're really getting to the scope right now. Yeah, does that make sense? This is just, yes, go ahead.
I guess there's only like one physical world, and so if you can have videos of it, multiple angles, as long as you reconstruct that one physical world, there are like voxels, then it's a finite element system.
Mhm. Yeah, and that there's a lot of, like even inside of this, you can construct a lot of, there's a bunch of these rooms in this building, and if we relocated to like the class across this room, I don't know if we could physically tell the difference. But in a lot of contexts, the difference doesn't actually matter in that case, even if I was to tell an agent robot to close a laptop in this room versus that room, it can ignore a lot of the stuff that doesn't really matter to the cache. But it needs to be able, if it can classify these things into groups better, it can figure out, okay, no, actually all this stuff is a part of that normal group of things I can ignore. But only once it really starts to experience all that diversity, all this variation to understand that, like a water bottle is a water bottle. It's not, if you're thinking about solving a task, you're just looking for that any water bottle classified object. Much more of what supervised learning tries to do when it's like classifying objects here, but we're going to also get into the fact that, well, when we're talking about robotics and planning, these objects are not just collections of pixels, they have dynamics and use inside of the environment, so we can get a little more information about them because of that. Okay, great. And this is really what we're trying to, one of the larger parts of what we're trying to solve. So, where are we going to get all this data? Any ideas? Now we need so much data, diversity, so we need to cover a whole bunch of things and enough to get the proper variances and classifications across any object. Your thoughts, how do you get all of the data that helps you identify whether or not laptops are the same or not?
Select that to experiment and select that. Or try to have something together.
Yeah, so like collect more data. In this case, I would say get some more experience, interact with the world. Yeah, so that's sort of leading into the next part. Hopefully no one is cheating a little bit and looking at the next set of slides, which usually answer a lot of my questions. Okay, there is supposed to be a video in this slide, but now I'm a bit scared to try and activate it so I don't corrupt the last version of working slides I have on my tablet. You're welcome to try and play it on your computer. It's a lovely one of just this nice local bot going around and cleaning up a room. And the fact that it's just like, we didn't use really any pre-training in that particular problem. Maybe I'll put like a picture in here in the future just in case the video doesn't load. But the idea is this agent is just, if we can do such a good job of making our algorithm well-formed and data efficient, we can just take the robot with the reward function it's got. We don't need to do zero-shot generalization, stick in that room and it'll learn to clean within the day. And that's another form of generalization. It's kind of like infinite shot generalization, but it works. In fact, it works better technically than like anything out there. If you can get an agent that can learn from interaction in its world and give it an objective, it can always just keep doing things. And mathematically, it should eventually discover how to solve that thing. Which is, less assumptions than doing zero-shot generalization. But the caveat is, all right, now you have to make a system that can interact in the world, which might sound like a bad thing, but it's what we do every day. We do it really well, and I'm just trying to get this to work on robots as well.
So he will learn to forget. But how we do, so we learn very.
It's true, actually. Well,
Problem of catastrophic forgetting. I read it once in the paper.
mhm.
I think they call it like that.
I usually think that the word catastrophic is a little bit strong. I mean, forgetting is forgetting, but yes, some forgetting is good. In some ways, I have forgotten up until this point, the larger effects of winter and how to deal with them. And then I get used to recovering how to deal with those, just like everyone is bad at driving for the first week once winter comes, because things don't quite interact the same as they used to. So our local physical model of the world changes because we go through different seasons. But maybe it's because we have limited capacity, and that's just something we have to deal with. Yeah. Yeah.
It seems like there's many important problems in which we want systems that assist with decision making, in which we cannot necessarily learn from interaction, either because it's too expensive to do so, or because we're coping with a form of irreversibility.
Okay.
So for example, I'm not going to learn from experience by driving into the left lane and crashing into a car, right? Like I have efficient reuse of knowledge in a certain way to avoid that.
Yeah, hopefully because someone told you not to do that. But someone's kind of distilled down a few of the rules for driving that are really general rules. It doesn't tell you about how to do this all the time. And I don't know if you've driven around in the UK where this rule doesn't apply very well. So a lot of these are still context dependent. I'll try not to be too much of a pain about the first one. It's okay, if it only costs money to be able to develop a system to interact with people, then that's not a problem to me. People are seems that people are willing to spend crazy amounts of money if they think it'll actually solve this problem. So then it's just money and time. And that's kind of research related, but it means that there's a way to get there. I think the irreducibility problem, or what I might also call this, is when you're training an agent that is learning, at least, or an autonomous RL agent, often it needs to be an ergodic agent, which means it needs to be able to visit every state. How do I know if I'm an optimal agent if I haven't tried everything in every state? There's a lot of states you probably don't want to visit. Also, at the same time, none of us in this room are ergodic agents. We cannot, as far as I know, let me know if you cannot rewind time. If you can, I will give you an A+, just let me know your secret. But otherwise, this is not how we typically learn. And so there has to be some way around some of these challenges. Maybe you can bake in some of these rules for large chunks of the state space. I think we always choose, or we're scientifically incapable of monitoring and measuring the rest of the universe, so we just don't worry about it and we get on with our lives. So those are two theoretical problems, but a lot of what we'll talk about is, okay, are they useful or are they practically going to be important for the task we actually want to solve? Yeah, we'll see. Some of these we don't have a definitive answer on yet. So that's where, but this is where we want to get into autonomous learning. For one, just going back to the comment from before, I don't think we want to spend our hours collecting data for our robots. I want our robots to be collecting data for us. So this means we want to make a nicer autonomous system that'll do this for us, even learn to interact with us over time and eventually learn how to do better things for us. And to be honest, that's an interesting area of research. We've done a few projects like that. They're complicated. But basically, we've got robots that exist inside of this possibly diverse and somewhat crazy world. We want them to be able to interact and collect their own data. And that's one way to be able to get around this. If we need tons of additional data for robotics, there's one way we can go and get it. And basically, we just need to figure out how to make some deep reinforcement learning, this little interaction paradigm. We've got some agent, it takes some action in the world, it gets back some reward in the next state as it unfolds. And then from this, it just learns how to take a bunch of actions to eventually get higher and higher reward. Someone in this room defines what the reward function is. We'll talk about that a little bit at the end of the lecture. The reason why this is nice is it gives us this nice autonomous learning agent that learns from this interaction. And it's good because, as some say, basically RL is the entire learning problem altogether wrapped into one. There's nothing else you're going to do about it. You don't need to separate anything into supervised learning. As long as you can figure this out, you have an independent learning agent. You can figure out how to do it so you can. And this, I would say, is a bit more ideal, especially if we want more scalable agents. Wouldn't it make sense to make more scalable, autonomous learning data gathering systems rather than depend on, I guess, us having to always collect all the data through grunt work? We'll see. And that's what I was already mentioned, some of this for being able to collect data in the environment, figure out which action by kind of computing the reward to see which ones are better, and then learning to repeat better actions. And then just a teeny bit on the math here, we're basically, so before we waved our hands a lot about generalization, in this class, we're still going to focus a lot on planning, which means that it's not just like generalization to a held cup. It's like there's going to be some path or trajectory the agent is going to follow, and we want it to still do well on that path or that new reward function, even under a different state or distribution. But this basically means a lot of what we're going to be concerned with and talking about is we've got some model that essentially induces a distribution over potential trajectories. And no matter what you might change in the world, we want that distribution over trajectories to still maintain a really high reward. So even if someone comes in and adds a couple of dots on the image that our robot is using for input, or if a bug flies into the screen or something like that, it should still get high sums of rewards over these trajectories. And that's more so what we're going to focus on here, since we need an interacting planning agent. Okay, does that make sense? Clear? All right, because we're gonna beat this equation with a stick like every single week and talk about like what doesn't quite work about this and where this can fail and how we can improve it. All right, but basically, so going back to this is our objective that we want to be able to optimize. Now we'll have some policy where we've got, the policy is basically this network in the middle. And now we're basically figuring out how to train this thing to be the thing that maximizes rewards. Here, I just have this self-driving car example for being able to turn right or left in this situation. But I'm going to talk a little bit more about, so this is RL, but I want to get into being able to talk about whether or not RL is extremely data hungry. Because as much as, like, I'm sure if anyone in here, like you dropped your laptop off your desk and it broke, you'd hopefully only need that one experience in your life to understand and never do that again. Most RL algorithms will need to do that around 1,000 to 10,000 times before they finally figure out that's a bad idea. So but the question is why does this take so many examples? This might make RL look really, really data hungry, but can we make it much less data hungry? It shouldn't need this many examples to figure it out. So this is true that RL can require this really large amount of data, but people were much better at essentially like exploiting the data that we get. When we break something, we have a much better credit assignment problem really quick and boost ourselves to not do that type of thing again. So how can we get that to work even better? And what I'm talking about for the next bit here isn't about exploration. It's literally if I gave you a pile of data that you experienced, how much can you learn from that data just by like revisiting it a lot, rather than having to go and collect more data or find something else that's novel. So maybe some of you are familiar with the Anne LeCun's cake. It doesn't taste that good. It's pretty mean to RL people. But the idea is, seemingly from this cake, the assumption is that RL is just this cherry on top. It doesn't add much, and it requires an enormous amount of data to get any progress. And a lot of progress lately has been made on, okay, can we figure out how to make RL algorithms that'll essentially be able to eat this cake faster or essentially consume more data? Okay, but what this means, so why is this happening? So this might sound silly, but supervised learning is great. It can do this fantastic thing where if you train on a batch of data repeatedly, it converges. RL can't even do this. For the most part, it would end up diverging in the policy because you end up fixating on this particular data set. It'll bootstrap itself. It'll usually, the network will go off to like positive infinity and the whole thing will explode mathematically in terms of statistics. This is where if you try to do something like this, a lot of on-policy algorithms could essentially only look at their same data about 10 to 20 times before it starts to have this type of divergence. After that, off-policy methods work better, but these can still end up with this type of divergence the more and more times it basically makes a pass over its own data. So this might be weird if you're more familiar with supervised learning, where it's like, well, I just want to make as many passes over your data as possible. But now I'm saying RL algorithms, at least deep RL algorithms, the more passes over your own data you make, the more likely it is your model diverges and is no longer useful. So this means that because the agent is generating its own data, it's effectively wasting the most, and we want it to be able to look over its data as much as possible, to be able to learn from things really well. Okay. Right. So this is from basically we want to figure out, we need to improve these algorithms such that we can basically squeeze the most information of the data that we collect. This is what I meant, like if we drop the laptop, we probably learn those bits of information really quickly, and we don't need to drop a laptop now in the other room, drop our laptop at home to understand that dropping our laptop was never a good idea to begin with, even in all these other states, doesn't really matter. Okay, does that make sense? This is like the picture on the right is like something supervised learning is great at, and RL, because of the dynamics of the way the algorithms work, have not been able to do really a good job at this at all. However, we're getting much better at that lately. So I guess I'll just go over a little bit in the next few slides. So how this works, what it's called in RL is called experience replay, which means that your agent collected some data, got some for loop that says I collected some data, I'll sample some batch of data, I'll minimize my reward, agent loss, whatever you want to call it for now, and then basically do this repeatedly. And what we're going to pay a bit of attention here is just this value K. Essentially, what we want to work really well is we want to be able to increase this K value to infinity. Okay, it should just be able to process over all of its data as much as we want until we're happy or the agent is already getting good performance, and then it can go and collect new data. So algorithms are basically trying to improve on this number. It's called an increasing replay ratio, if you happen to see that term more on the internet or in research. Okay, does that make sense? This is sort of, I don't know, for people that tend to also like fixate on stuff. The amount of time you replay situations in your past in your head until you feel like you finally captured everything. This is even something I think they do in a lot of like professional sports, where they'll sit down and like rethink through the whole process of the game and whether or not they'll take certain actions versus other ones. Kind of like doing this data processing again and again. And then in the class, we'll talk a little bit more about, okay, I want this to work. I also want this to continue working if I make my network bigger and bigger so that I can ingest even more information and it's not capacity limited as well. Unfortunately, surprise, surprise, when you make this bigger, this problem gets even worse really fast. So, I don't know, the size of networks that you see people using for RL research is nothing like I don't know, a point on a needle or something compared to what's used for large models these days, because it's having to deal with a lot of the dynamics and these training processes. Okay. So, any other questions? Okay, remember on Friday, we're at Mila in the Agora room. I'll post something on Discord with like the address on how to get there, so everyone knows how to get there. And I'll see everybody there. All right. Thanks. It's from 2 until 4. Thank you. All right, take care, everybody.